All right, so this morning we will just have Q&A. All right, I'm not going to go take the whole clinic session to go to the continue where we were. We've already done quite a few of the past year questions. So those of you who were not able to join us earlier can go to YouTube and look at the videos over there. All right, yeah. Okay, so we have Q&A. Any questions? Questions? Any questions? No questions. Hmm? Are there any questions?
Hello, Prof.
Mm-hmm.
I want to ask um, about the about the static state value k. This k, sometimes we use the formula limit s equals 0. Then we use s times or multiply gs. Sometimes it's no use only gs. Why here is like this? This one is value how to say the static.
You mean the value of the steady state value k?
Yeah. You can see the lecture 9, then 50.
Okay,
Here is no
let me
s.
go to it. Let me go to it. Lecture 3, is it? No. I got several questions here. I'll answer yours first. Which lecture is it?
Lecture 9.
Lecture 9, is it?
Here is then
Okay,
lecture.
go to lecture 9 first. Hang on. Lecture 9. Okay, which slide?
Lecture 9. Boundary port. Uh, Lecture 9. Yeah, correct. And next. 50.
Which one?
50. Yeah.
Yeah.
limited s equals 0, right? Here is no s, but before lecture 8, and before we calculate the state gain, we must multiply the s.
No,
Why?
this is not using final value theorem.
Oh, here is not.
No, no.
Oh, okay.
You mix up with final value theorem.
Oh,
Okay.
so it's different, right?
It's correct.
Oh,
This has nothing to do with final value theorem. Okay.
okay. Thank
All
you.
right.
So
Okay.
final value must multiply s.
Yes.
Oh, okay.
All right.
Okay.
Okay. So I have another question here, which is from, okay. Could you explain the Fourier transform of differentiation and integration in lecture 3? Okay, let's go to lecture 3. Lecture 3. Where is lecture 3? Okay. Okay, so these are all properties of the Fourier transform. Okay, we are not proving all this. We are just using this, okay? All right, I told you all already that we don't expect you to prove this. We expect you to utilize it, all right? So when you differentiate a time signal, so if you look at differentiation, which is here, let me remove this one first. Differentiation. Okay, so when you differentiate in the time domain, in the frequency domain, you multiply by j2 pi f. That's all you need to know. All right. Similarly, if you're integrating the time domain, this is what happens to the spectrum of x in the frequency domain. So that's all you need to know. All right. And that's why when we look at the table over here, these are all summarized in this table. There you go. Differentiation, you multiply. Integration, down here. Integration, you have this guy. All right. Okay. So that's what happened to the spectrum when you differentiate or integrate in the time domain. All right. Okay, the next question that I have is on 2023 1718 S2 question 7. 2023. Hold on. Let me go to the thing first. 1718. Okay, hold on. S2. And you want question. I lost my chat window. What happened to my chat window? What happened to my chat window? Question 7, I believe, right? Please, can you, I don't know, I lost my chat window in my main screen. If you're asking me a question, please can you to everyone so I can see on my other on my other screen, because I lost my chat window here.
Okay. Question 7 and 8.
This one, right?
Yeah.
Yeah. So please ask the question, not directly to me, but to everyone so I
Okay.
can see. Okay, what's the question, Timothy?
I want to check part B's both phase plot graph.
Okay. So if you look at this question, let me expand it now. Okay. Oh, come on. Okay. So we can see that as we scan from left to right, the first subsystem is a differentiator, as you can see here, right? A differentiator, right? This is the first subsystem. Is a differentiator.
Yeah.
Okay. Then you have a corner frequency of 1 radian per second, as you can see here. Okay. So the second subsystem is a pole because it pushes it down, right? It pushes it down. Huh?
Yes.
The third subsystem, another corner frequency here at 10. It pushes it down again. Okay. But you notice that it pushes it down. The slope of this guy is steeper. You see, over 1 decade, this is 1 decade from 10 to 100. That's 1 decade. It goes from 20 to minus 20. That means over 1 decade, it has changed minus 40 dB. That means this is a repeated pole.
Really one time.
Over 1 decade, it has changed for 40 dB. Right? It's a repeated pole. So now you know where are the corner frequencies. You know what are each of these subcomponents. All right. So for every one of these subcomponents, you have a plot. Remember those 6 plots that we have, those building blocks? GS is K, GS is a differentiator, GS is an integrator, GS is a pole, GS is a zero, and GS is a underdamped second order system, right? Those 6 things. And each of those, we had both the magnitude and phase plot. So basically, you take the phase plot of G1, G2, G3, and so on. You plot it and add it up together, each of the phases. You got it?
Yeah. How about the plot for the repeated pole? I'm not sure where to start.
It's the same as for a pole, but instead of going from 0 to minus 45 to minus 90, you will go from 0 to minus 90 to minus 180. That's the only difference because it's repeated. You see, the phase will change over 2 decades, right?
Yeah.
Okay. At the corner frequency, it will go down to minus 45. But now it's repeated. So at the corner frequency, in this case, the corner frequency is 10, as you can see here. All right. So instead of going to minus 45 at 10 radians per second, it will go down to minus 90. But it will still change over 2 decades from 0 to minus 90 at the corner frequency to minus 180 at 10 times the corner frequency.
So is it still a sort of a Z shape, but
yes, it's just that the change in phase is double because of the repeated pole here.
Oh, okay.
That's the only difference.
Prof, if the dB reduce 16, meaning the phase 3 times, right?
Yes, yes, because it's always multiple of 20.
Okay. I want to ask the same like this question, but this one is a magnitude.
Okay, hang on. Before you continue, Jia Wei is asking, how do I know it's second order? As I mentioned, it's second order because this slope here is minus 40 dB per decade. If it was not repeated, the slope will be minus 20. Okay, Jia Wei?
Prof, so it starts out at 0 as a flat line, then in between 10 to 100, then it becomes a diagonal line.
That's right. Yeah. So that was in what's it, chapter
10.
10. Yeah. The summary is there.
Okay, so but there are no curved edges in between.
No, because all these are asymptotes. So these are all approximate behavior.
And then it ends off right at 100 radians per second.
Yes. So that means if you were drawing the phase, so in other words, if we were drawing the phase, so according to this guy here, you can see that G1, let me write it down so that it's easier for you guys to see. So you can see that G1 is a differentiator. It will be KD times S, G1. So what is KD? So you look at omega equals to 1. At omega equals to 1, it is 20 dB. So 20 dB, okay? That means 20 log KD is 20 dB. So KD, all right? That's the value there, okay? So we see that at, let me put this, at omega equals to 1, okay? The magnitude is 20 dB. Okay, so what that means is 20 log KD is 20. So KD is 10, 20 over 20, which is of course 10.
So G1 is equals to S. It's just equals to S.
So G1 will be 10S. Okay, that's how you determine the differentiator gain KD.
Okay.
G2, as we say, is a pole. So we have a omega 1 is at 1, right? Okay, so tau 1 will be 1. So G2 is a pole. All right, 1 over S plus 1. So that's G2. And G3 is a repeated pole. So omega 2 is 10. Tau 2 is 1 over 10. So G3 is 1 over 10 S plus 1 whole thing squared. Repeated pole. Okay, all right. So now when you plot the phase plot, okay, this is going to be log omega. So this is angle G, okay. Most of them will be negative. So let's say this is minus 45, minus 90, minus 135, minus 180. Okay, let's do that. So G1 is at 0, correct? Because G1, the plot for this one is not 0, at 90 degrees, because it's a phase, 90 degrees. So let me also put up that thing first, because it's a differentiator. So this is 45, this is 90. So G1 will be up here, 90 degrees.
Prof, how come the horizontal axis, why is it labeled as log W and not
Because it's a log
F?
scale.
Can I put F radians?
No,
Oh.
it's radians per second, but it's a log scale. That's why I put it log there.
Oh, okay. Okay.
You see the log scale? Yeah. It's a log scale, right? I shouldn't put omega there. Okay. All right. So this is G1. Okay. So let me just put the others, the other things first. Okay. Let's say this is let me just put it down. So this is 1, 2, and 3. So this is 1, 10, and 100, right? Okay, this is what it is. So G2, as we say, is a pole with a corner frequency at 1. That means over 2 decades. So let me draw G2 here. At at the corner frequency of 1, it will be minus 45. That one decade later, it will be at 90 over here. And 1 decade. So G2 is this guy. This is G2. Okay, that's G2. Then we have G3. Let me take another color for G3. Okay, So the corner frequency is 10 now. All right. So 10 at 10, that means, and it's a second order. Second order, that means it will be here. At 10, it will be minus 90. 1 decade before that, it will be at 0. And 1 decade after that, it will be at 180, which is down here. So this is this line here. This line here. This green one. So now you have to add all this together. These three subsystems together. So if you add it all together, okay, you will have the following. Let me see if I got another color. Okay, I got a blue here. Okay, so what happens is that this is at 90. So we start 0 and 90. We'll start off here at 90. Now 90 will start to minus 45, so it will come down to here now. Okay, because this one is still at 0. The green one is still at 0 here. It will come down to here. All right, then 90 minus 180 now, because you got the green one minus 90, the red one at this point at 10 also minus 90, so minus 180. The positive is plus 180, so it will come down to here, this point here. Okay, then here again you got minus 90 minus 180 is minus 270, plus 90 will be 270. Okay, 270 minus 90 will be 180. Okay, so basically you will have this from here to here, then it will come here to here. Okay, and then hold on, over here it will be at minus 180. Follow here, and then this. There is the blue line. So that's how you combine them together.
Oh, okay. Yeah, I
Yeah.
could not get I did not know how to combine them yet.
Yeah. You find all these key points, you know, so you know how to draw your lines.
Okay.
Okay.
Yeah.
Yeah.
Prof, for the part C, right, there is a delay of 50 meters, but ms.
That part you don't worry, because I didn't cover delay. We took it out of the syllabus.
Oh, okay. So that means the following, I'm not sure. I didn't look at the following part D. So that means you cannot do that
We
also.
didn't teach you that. Yeah, we took out some things. Because look, this was like 4 years ago.
Right. Okay, can.
How to combine? I have to repeat the whole thing again. Okay, first thing is that you need to draw each of the phases, each of the subsystem, right? So G1 is a differentiator. Differentiator has a phase of plus 90 degrees. Okay, which is the brown one. G2 is a pole with a corner frequency of 1. So at the corner frequency of 1, the phase plot will be at 1, omega equals to 1. It will be minus 45 degrees. And 1 decade before it, it will start at 0. So that is the red curve here. All right, at 1, it is minus 45 degrees. 1 decade before that is 0. 1 decade after that is minus 90. So G2 is this red curve. G3 is a repeated pole, okay? Which means that at the corner frequency, which is 10, it will be at minus 90 because everything is double, it's repeated, minus 90. 1 decade before that is 0. 1 decade after that, which is 100, will be minus 180. So now you have the brown, the red, and the green. So now you find all the key points. So at this point, you have plus 90, 0, and 0. Plus 90 plus 0 is still 90. So I draw the first blue dot here first. The next key point is here where there are changes. You have plus 90 for the brown, 0 for the green, minus 45 for the red. So 90 plus 0 minus 45 is 45, which is this point. Okay, the next turning point is at 10. Again, you have plus 90, which is the brown. You have minus 90 for the red and minus 90 for the green. Plus 90 minus 90 minus 90 is minus 90. So you got this blue point. Okay, and finally you have at this 100. At 100 you have plus 90 minus 90 minus 180. 90 minus 90 minus 180 is minus 180, which is this point. So now you join the points. Okay, Ching.
Prof, just to check, the equations for G1, G2, G3, they're completely independent of how the phase plot should
Those
be,
are
right?
your six basic building blocks, remember?
Oh, sorry, I mean no matter what equation it is, as long as you can identify that they are differentiator, pole and repeated pole, the phase plot will always be the same standard.
Yeah, it's based on the
okay.
It's based on what these elemental subsystems are.
Okay.
Okay.
Yeah.
So G is G1 times G2 times G3. That's the combined system.
Okay, so like for example, differentiator will, let's say
Differentiator will always be KD times S.
Okay.
Same like integrator. Integrator will always be KI divided by S.
Okay, can. Yeah.
Right?
Pro.
Yeah.
G3, the graph of the phase, I still have some no understand because here is 19 degree. 19 degree is first order. Here repeat should be 180. So how this job, your job?
Okay, so if you have a pole like G2, at the corner frequency is minus 45, right? G2. At the corner frequency, which is 1, is minus 45 here.
Yeah, clear. Yeah. G2
So
clear.
if it's a repeated pole, at the corner frequency, instead of minus 45, it will be minus 90. See? At the corner frequency of 10, it is minus 90.
Yes.
Double, double. 1 decade before that is 0.
Yeah, correct.
1 decade after that, instead of 90, minus 90, it becomes minus 180.
Yes.
That's all. Nothing, no secrets, no mystery there.
So the right color, no.
So the green color, now I draw the blue. You couldn't see the green inside here.
Follow the blue, right? Blue.
Yeah, the final one is blue.
Oh, okay, final is blue. Final one combine is also no blue.
The combine is the blue, which is the question that Jing Ying just asked me just now.
Yeah. Combine is blue.
Yeah.
Oh.
Yeah, blue is for G. It's the face of G. That's why I said face of G.
So, right color is only for G3, but no.
Red color. Okay, I repeat. Yeah, I write it down. This is the face of G1.
Maybe you can mark here. Yeah.
Okay. This is the face of G2.
G2 clear.
Okay. And green you cannot see here. Green is here. This is green. Okay, I put here. This is the face of G3. Okay, it's a bit light like this. I don't have a thick green one. That's the face of G3. So I'm combining the brown, the red, and the green. I see if I can get a thicker green. I got a thicker green here. This is better. Okay?
Okay.
So I'm combining the brown, the red, and the green, and then I get my blue.
Okay, understand.
Okay, so how, as I said, to get your combine, you find all the where are all the corner frequencies. Those will be your points to join up later. Okay.
Okay, I understand here.
Yeah,
Uh,
yeah.
and I want if the question are given the combined graph in this
Yep, you can also work backwards.
how to find the transfer function?
You can also work backwards. Yes, we have questions like this as well in the past years. You can work backwards as well.
Okay, later.
Yeah.
Yeah.
Okay.
Prof.
So the always remember, always find how you use those 6 basic functions. All right. And at the same time, identify where are all the corner frequencies. All right. The 6 basic functions, again, as I mentioned earlier. All right. The 6 basic functions, if we have GS is KDS, which is KDS, this is your differentiator. GS is KI over S, is your integrator. All right. I forgot to mention this one. GS is just a constant. GS is just a pole, 1 over tau S plus 1. And GS is a 0, tau S plus 1. And finally, under them, second order system, omega n squared over S squared plus 2 zeta omega n S plus omega n squared. Those are your 6 building blocks. That's all the ones that we have been using all along. So whenever you have a corner frequency, it tells you what these values are. And in the case of a differentiator and an integrator, the value of KD or KI is found at omega equals to 1. We are always
Prof.
using these 6.
Prof.
Yeah.
Check with you for the G2 your G2 graph.
Yeah.
Okay, I understand the G2 graph is a pole, but based on your previously what you draw, right? It should be start from 0, then it's horizontal line to this 0.1 omega
before
c.
0.1, before 0.1. So again, always start at the corner frequency. Corner frequency is 1 is minus 45 degrees here. 1 minus 45 degrees. 1 decade before that is 0. That means anything to the left here, all 0. That's it. Then
But,
1 decade after which is 10, it will go down to minus 90.
Yeah, Prof. But the thing is, based on your graph, right? It should be from 0 horizontal line first, then go down to minus 45 degree. But yours is
So
straight away from 0 go down.
No. Okay, I didn't draw it lah. If you like, I will draw the red line here. Okay.
But the line that start to go down should be from
0.
0.1, right? Based on what you...
Yeah, 0.1 here.
Oh, this one not 0. I thought this one is 0.
I'm saying it's 0 degrees here. 1 decade before that, this number here is 0.1 radians per second.
Oh, okay. Because I thought that one is 0.
No, there's no 0 on the log graph.
Okay. Thank you.
Okay, unless you have a newly invented log graph. There's no 0 on the log graph. Okay. Any other question related to this? So you see, it's very systematic here. There is no uncertainty about this or that. It's always using these 6 basic functions here all the time. All right, and all these 6 basic functions always depend on the corner frequency, except for differentiator and integrator, because differentiator and integrator does not have a corner frequency. It's always like that. Okay. Okay, I have another question. How to combine this is okay. This is regarding which lecture? How to convert to phase? Lecture 10. In fact, lecture 9 and 10. Lecture 9 and 10. Okay. how to do the phase. Now, if you're still not sure, please can you go to the YouTube and look at clinic, the lesson 25. All right, I summarize everything about signals in lesson 24, and I summarize everything about systems in lesson 25. Okay, let me just show you. Let me just stop this for a moment. Okay, let's see. Let's go into the Lumina YouTube. Okay. All right, let me share the screen again. Where is it now? Look, this is the playlist for the BTech group. This is the playlist. Of course, the BTech will you only see your own list, huh? Okay. Either way, it's still the same. Let's take the playlist of BTech group. All right. Lesson 24 here is all about the key points of signals. Lesson 25 is all about the key point for systems. Okay, if I play the video now, it's very jerky because Zoom doesn't like it when you play it, but basically that's what it is. So let me just give you an example here. Okay, let me turn the volume down. The volume is off already. All right, so all the revisions are inside here. So where are we now? So we're probably at this point here. You see, I give all the key points here. This is for K, GS is K. This is for integrator. This is for differentiator, and so on. All of it is there. You see? All right. And then we go on to pole and zero. All the revisions are here. This is all the essential points that you need to know regarding systems. All right, I've turned on the video right now. I turn off the audio, otherwise it's too noisy. Please go to this tool to do your revision. I went through this already. Okay, let's see if there's another question. Could you cover Q8A as well? Okay, let me turn this off. Hold on. Stop sharing. Okay, where is my Q8A? Hold on. All right. Determine hey, I already determined the transfer function. You know G1, G2, and G3 already. G will be G1 times G2 times G3 lah. That's all. Okay.
Prof, that's question 7.
Huh? Oh, that's good. Could you cover Q8A2? Okay, Q8. Hold on. 7. 118. This one is it? Okay. Yeah. Let me make it bigger so it's easier to see. Okay, so determine the transfer function. Okay, so it's already told you that this is the unit step response of a second order system. Now, what second order system gives you this response? It's an underdamped system, right?
Yeah.
Okay, it's an underdamped system. So for the underdamped system, the formula is already given to you over here. Okay, there you go. So that plot over there, that plot that you see is basically this equation. Okay, it's basically this equation. All right, so you have to determine what are the parameters of this equation. Okay, remember I gave you the step-by-step derivation of all these parameters. I did it at least 2 or 3 times. At least, and again, it's also in revision in lesson 25. Okay, so when you want to derive what is K, what is omega n, what is omega d, what is sigma, what is phi, all right, it is all from that graph, from this equation. Okay, so these are all the relationships. Okay, so given this is the relationship, we come back to the question now, which is here. Let me kill this one. All right, given this relationship, what are the things that we can find? We can find what is K, because K is a steady state value here, which is 2. So K is known. If you take one cycle, let's say from this point here, okay, to this point here, you can see that one cycle is 3 seconds. So that means you know TD. If you know TD, you know FD. If you know FD, you know omega D. All right, so you know omega D now, you know K now. Now, this envelope here, it says it's e to the minus pi t over 6. E to the minus pi t over 6. If you look at the formula, e to the minus sigma t. So you know sigma. Sigma is pi over 6. So there are 3 things that you can infer from the graph. Okay? So let us put down what are these 3 things. Okay, let's put down this equation first, because otherwise I've got to keep flipping the screen. Huh? All right, so this equation y step, I'll switch over in a minute. Okay, let me just copy it down first. K into 1 minus omega n over omega d e to the minus sigma t sine of omega d t plus phi. All right, and then the other formula that we need is that sigma equals to zeta omega n. Let me write down all the formulas first, because I don't want to keep flipping the screen. Huh? Here n square root of 1 minus zeta squared and 10 phi is equals to omega d over sigma. Okay, now let me switch the screen. Okay, so I reproduce the key formulas that we want to use. Huh? Okay, we come back to the question here. All right, so as I said, the steady state, according to this equation, if you look at the equation, when this t tends towards infinity, this whole thing goes to 0. You're just left with k. So from the plot, you can see that k is 2. That's known already. All right. Then you see is e to the minus sigma t. And you're told that you have e to the minus pi over 6. So that means we also know sigma is pi over 6. And then we know that the sine wave is a frequency of omega d. So how do I determine omega d? I see one cycle. One cycle will be from this point here to this point here. That's one whole cycle. And that is 3 seconds here. So we can see that from the graph, the period is 3 seconds. So that will lead to FD, which is 1 over 3, which will lead to omega D, which equals to FD over 2 pi. FD is 1 over 3, so it's 1 over 6 pi. So you know omega D.
Prof, for this kind of unit step response of second order systems, to find TD, do we always start at
one cycle, you see
0?
where is the beginning? You find a convenient point of one full cycle.
Because it gets harder and harder if you
the points are very easy to identify. This is 0. This is another 0 here. There's one full cycle of a sinusoid. You pick the most convenient and then you round it off. That's it.
Oh, okay. Okay, can.
Okay, I mean, you could have picked this point over here and this point, but it's harder to see lah. You understand what I'm saying? If you pick this point,
Yes.
maybe, okay, this is about 1.8 to, you can see here, from if you take this point here, 1.8, okay, to where is it now? Up to here, 4 point something, I don't know. All right, so it's harder to see, you see. But you pick this one, it's easy, what? Start here and end here, right?
Yeah. Okay, can. Thank you.
You pick some convenient point to find TD, no? Okay, so out of this equation, we already found K, we found omega D, we have found sigma. So the only two unknowns now is omega n and phi. All right, so you use the equations here. You know sigma. So from the first one, sigma is, where's my sigma? Sigma is pi over 6. Pi over 6 is zeta omega n. So that is equation 1. Then the equation 2, omega d is 1 over 6 pi is omega n square root of 1 minus zeta squared. This is equation 2. So from these two equations, you can find zeta and omega n because there are two unknowns, two equations. All right. And finally, to find phi will be arctangent of omega d over sigma. Omega d is known. Omega d is this guy, 1 over 6 pi, and sigma is pi over 6. You can work it out. Okay, is that, I don't have to do all the details, I'm just telling you all the steps.
Yes, Prof. Can I just check again? So sigma, how do you identify that it's pi over 6 from
Here.
the asymptote graph?
From the graph here, see? E to the minus pi over 6t, and that belongs to this guy here. So that sigma is pi over 6 here. Can you see it?
Oh, okay, okay, can. Yeah.
All right. It belongs to the exponent term. Yeah, I lost my chat window. That's why I always have to have two computers running at the same time. I don't know why we have this problem. All right, everyone. I think I've answered all the questions, right? From 1718 Q6. Later, can you explain how to convert HF block to HT for Q6A? Okay, okay, we're done with this, QA, question 8A. All right, everyone?
Prof.
Yeah.
Omega D is equal to F divided by 2 pi.
Yeah, omega equals 2 pi F. Is it omega? Yeah, sorry, it's the other way around. My apologies. Yeah, omega is 2 pi F, not the other way around. 2 pi F D will be 2 over 2 over 3 pi. My apologies. So this is omega D. So this is 2 over 3 pi. No, sorry. Let me write this again. 2 over 3 pi divided by pi over 6. Okay. Thank you. All right. Are we good with this AA? Then AA? Timothy?
Yes. Yeah.
All right. Now, just in case, B asks you for the post. Okay, you come back to this guy again. Second order. The posts are given by this guy. You already found sigma. You already found omega D. Those are your posts. You don't have to solve for it. Just use this formula. Okay. All right. Then let's go to the next question, which is question 6, right? Yeah. Okay. Okay, so what was the question? How to convert HF block to HT? How to convert? Why do you need to convert to HT? The question never asks you to convert. Okay, so what happens here is that you have the signal X multiply going through this system H. So in a frequency domain, X hat is capital X times capital H, X hat. Okay, in the frequency domain, you have X hat will be X times HF in the frequency domain. You don't have to convert. All right, but HF has these three things. For negative frequency is J, at F equals to 0 is 0, and for positive frequency is minus J. That's what is HF. All right, that's the HF. So that means when you calculate this X hat, you need to break this X hat into three parts because negative frequency, positive 0, and positive. So basically this becomes, for negative frequency, it will be J, becomes JXF. For F less than 0, 0 times 0 is 0, and minus JXF for positive frequency. That's what happens. Those are your three parts. Okay? Those are your three parts. So if you're going to plot the whole thing later, because it's asked you about all these expressions for X, etc., see? Okay? Right? Because he asked you to plot the spectrum of YF. So YF is this guy, X1 cos plus X hat sine. That is what is Y. All right. Now you notice he didn't ask you to write down the expression. So you have to understand what is happening here. You have X here. Let's do the top rail first. The top. X here multiplied by cos will mean modulation, which means that the cos is two delta functions at plus and minus FC. Plus and minus FC. Right? So this, what happened will be the spectrum of X, which is given in here, which is a bandpass signal. The spectrum of X will be replicated at plus and minus FC. That's what happens on the top rail. Okay. In the bottom rail, you have two parts here. You have this guy here. All right, XF again. But XF is changed by this HF according to this. So it becomes this guy here. All right. And then you multiply with the sign. All right. So you have to do this part by part. Okay. So the top, let's look at the top first. The top is X1 is XT times cosine 2 pi FCT. That means X1F will be XF convolved with 1 over 2 delta F minus FC plus delta F plus FC. That means this becomes 1 over 2 X of F minus FC because of the replication plus 1 over 2 XF plus FC. So that's the top. All right. So basically what happens is if you draw the top, this is at FC, this is at minus FC. All right, and you're replicating this guy here, replicating this guy here at plus and minus FC. So if you replicate it at plus and minus FC, all right, you will have these two guys here, replicating at plus and minus FC, not to scale up, but just to illustrate the point. So this will be X1. This will be X1F. Okay, now we can do the same thing for the bottom rail. Okay, for the bottom rail, we have to get X hat first. X hat we have already got this here. Okay, and then from there we see that we multiply by sine. So we have X hat T times sine again 2 pi FCT. So all right, let me call this X2. Let me call it X2. Give it a name because it didn't give a name there. So X2F will be X hat F convolve with 1 over 2J into delta F minus FC plus delta F plus FC. Okay, so what happened will be X hat will be replicated because of the convolution at plus and minus FC. Okay, so for the plus part, which is this guy here, F minus FC, for the plus part, we know that you will multiply with minus J by this. Okay, for the minus FC, it will be multiplied by JXF. That's what we know. Okay, so if we do that, and then the J and J will cancel. So let's do the plus part first. The plus part is this guy. Plus part will be minus JXF, my apologies, because this is plus, convolve with delta 1 over 2J delta F minus FC. That's the plus part, plus FC part. Then for the negative FC part will be JXF convolve with delta F plus FC. This is what happens. So if you do that, the J and J will cancel here. Similarly, we got 1 over 2J here also. All right, so you will get minus X of F minus FC here plus, I forgot my 2, X of F plus FC. This is what you get. So now you can draw X2 now. Okay, so let's draw X2. Same thing, huh? So let me draw it here. In FC minus FC. This is F. I'm drawing X2 now. So he says here that for X2, this is inverted. So I have this guy here. I hope I get it right now. And for plus, it will be here. Okay. So now you're going to add X1 and X2. Okay, so you're going to add X1 and X2. I should align it a bit, but I have to shift it. Okay, I have to add them, which is what it's telling us here. YT is adding them together. All right, I may have got something wrong here. Let me just see. I got something wrong here because when I did this operation, what happens is that well, you multiply by J because of the positive and negative of, I forgot that this have to be flipped because of the multiple X hat here. All right. what happens here is because the positive part get flipped down. Actually, it's flipped down. All right, so theoretically this is not correct. So the positive part got flipped down, the negative part got is still positive. Okay, it should actually be my apologies. Let me see this how. So it should really be like that and like that. Similarly, over here, all right, it will be the other way around. Okay, got flipped the other way around. Yeah, this should be up here. Should really come like that. It should be the green guy. Okay, so what happens is that for the lower frequency, one is positive, one is negative. This positive is negative. This is positive. So one of them will get cancelled out, is it? One of them will get cancelled out, leaving you only with the outer ones. So YF will actually turn out to be like this. So if I draw it, FC minus FC. So YF will turn out to be just this guy here. That's what happens. So this problem is a bit complicated because of this operation here. Okay, so the whole thing, and that's why they call it, this signal called a single sideband signal, as you can see here. Because one of the bands here, there are two sidebands here, one of the bands have been removed. Okay, one of the bands. So this is what is YF. YF. And the bandwidth will be, as you can see, 80. This will be 80. Okay, because it's from 20 to 100, that is 80. I hope that explains it, huh? Yeah, that's right. 80.
Prof.
Yeah.
Okay, so when XT go through your H, right, you'll become square block, left side is positive, right side is negative. Right?
Yeah, it flips it lah. It flips
Correct,
it.
correct. You only flip the more than zero parts.
Yeah. So
Because,
you can see here, the positive part is flipped because of the
oh,
minus J.
Okay, okay. So
all right, negative remains on top. Yeah.
Correct. So that's your X hat, right?
Yeah, X hat. Yeah.
And then after that, you go to your sign. The sign is convolution. That means you replicate this signal at two frequencies,
yes.
right?
Two, no? These two.
So the right side, how come become the other way around?
Because I did not show you all the steps. So this one, this one you have to be very careful here. You have to be very careful here. Okay, it flips it around. Yeah.
So that means flip the right side the other way.
Yeah,
is
you flip the inner one in this case.
It's because of your minus J
yeah,
there.
because of the minus J. Yes, yes, yes. So it's not very obvious when you do this now. Huh? Okay, so this expression is not completely correct. So, this expression is not completely correct. Okay. Yeah. Let me just check. 17, 18, 17.
Prof, for X2F, X1F, and YF graph, is the numerical height important?
The height will be half lah, because you can see here, I derived the half here. So this one will actually be double because you're adding, will be 1. The green one, the one here will be 1 because you're adding. You're adding this one and this one become 1. Okay. Become 1. Okay. All right. All right, any other question?
Prof,
Yeah.
how come your X2F, the minus JXF is belongs to this F minus FC? How come not belongs to F plus FC?
Wait, let me just see what's happening here. Give me a minute. I just want to check whether I've done it right. Okay, let me flash the thing for you. Yeah, we have the details here, which actually works out everything in detail. Oh. Yeah. Oops. Too much. Okay, I think this is good enough. Okay. So here's the thing, All right. So first of all, we have XF, which are the two racks, as you can see here. All right. The center frequency is at 60 plus or minus 60, as you can see here. The width is 80 here. The width is 80. All right. Halfway will be 40 lah. So 20 plus 40 will be 60. So the center frequency is 60. All right. So rack F plus 60 over 80 is this guy here. Rack F minus 60 over 80 is this guy here. All right, so that's part A. Then you want to find a time domain expression of xt. So if you do the inverse Fourier transform of this, you will get the two sinc functions. All right, over here. Xt will be 80, sinc, rack becomes sinc, shift in F becomes exponent. Similarly, this one will have, all right, I took out the 80 sinc already, the two exponent terms, which can be converted into cosine. So that is your xt over here. Next, as I said, x hat is x, capital X times capital H in the frequency domain. All right, so you have this guy. All right, and given HF, you can see that the negative part is positive, plus J. And for negative frequency is minus J. This is what you have. X hat. Okay, all right, X hat. Although we don't need to derive xt lah, okay, but anyway, this is X hat, F. All right, then next thing is, we know have YF. YF, as you can see, is XF convolved with cosine on the top. This is my X1 just now. X2 is X hat convolved with the sine. Just multiply by sine t in the time domain is convolution in the frequency. Okay. All right. So when you convolve with the cosine here, all right, you move X to plus and minus FC, which is these two guys here. All right. Similarly for X hat, which you had derived out here, X hat, all right, you convolve with the sine, you'll be 1 over 2j for the moving to the right and to the left. Now, if you substitute all the racks inside here and clean it up, you get this guy here. If you substitute all the racks inside, it didn't show all the steps now. All right, so you can see that the width of the rack is still 80, which means the bandwidth is 80. All right, And now you can see that the frequency is at plus and minus 1940. 1940. So this will be the detailed workings. 1940. All right, given that FC is 2000. All right, so those will be the details. So if you substitute the FC inside, then it's clearer. FC of 2000. Yeah, basically one of the sides cancels out because of this operation. One of the sides cancels out. That's what happened. How to know which HF we should use? All right. So if you look at this, it's because of this function. How do you know? Because it says for negative F, negative frequency, HF is J. So if you look at the convolution here, right? For this part here, for this part, because it's X hat convolved with sine. Okay, so you have the positive part and the negative part. The positive part is delta F minus FC. The negative part is delta F plus FC. So each of this will shift the X hat to these two positions, will shift to these two positions. All right, so that's why you see here, this is the positive F, this is the positive F, and this is the negative F. All right, of course, we haven't substituted for X hat yet. X hat is this guy here. X hat is this guy here. So now if you substitute in, of course, the J's cancel. You just substitute it inside. So for this part here, all right, when you substitute inside here, you can see that wherever we see F, it will be replaced by F minus FC for this part. Similarly, for this part, wherever we see F, we will replace by F plus FC. That's it. Substitution of the variables. Substitution of the variables. Okay. So actually, to you have to expand this out. Just substitute all the capital X and the capital X hat now, and then substitute the variables and work it out. And so certain things will cancel out as a result of that. So when you substitute these terms inside here for capital X and capital X hat, each of these will give you two terms. This will have two racks, 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 and some of them will cancel out. And that's why you're left with just this guy here. So you substitute in. We didn't show all the steps here because it's each of the X and the X hat had two racks inside there, right? See, you have two racks inside here for X. For X hat also, you have two racks inside there. So each of them will. So you have eight terms inside, and then some of them will cancel, leaving you with just these two. Okay, that will be the details. All right, let's move on to any other question. Anything else?
Prof.
Mm-hmm.
Then for question 5, because I see the question, there's no numbers, everything are just letters. Anyway, how to start this question, number 5.
Number 5. Hey, I thought we did this already.
No, not yet. Last time we did question 1 to 4.
Oh,
Then we stopped already.
okay, let's look at it, huh? So we have a direct delta function usually cannot be implemented in a practical circuit. Instead of sampling a signal xt with a comb function, natural sampling takes the samples of xt by multiplying xt with the signal yt. So if you look at yt, it is a square wave. Huh? Okay, it's a square wave where it's made up of racks of width t0, as you can see, and this replicated every ts seconds. Okay, that's what is yt. So that is the obtained sample signal will be xs is x times y, which is this guy here, where ts and t0 are both positive constants and ts is much greater than t0. Okay, assume that x is a real baseband signal with bandwidth b, and capital X is its spectrum. The sampling frequency fs is equals to 1 over ts. Find the spectrum of y. So that should be straightforward because you have a periodic signal. So basically y looks like this. Okay, so y basically looks like this. Because it says ts is much greater than t0. Okay, and t0, so this is yt. So this width here is t0.
Prof, you got to zoom out. Huh?
Oh, I got to zoom out more. Okay, that's yt. Okay, so yt, it says is summation k rect of t minus n t s over t0. That's what it's saying. All right. So we are required to find the spectrum of y. So what we do is that we will use the concept of generating function, right? If you use the concept of generating function, basically we have a rect of width t0 and we replicate it. What do you mean by replicate it? Then that means basically you convolve with a comb function. So this can be rewritten this way. Rect of t over t0, that is your generating function, convolve with a comb function. Ts, yeah. Right? Both say the same thing. Now, once you put it into this form, then to obtain the Fourier transform is very straightforward. All right? So then YF, this guy, right, becomes sync. So it's T naught sync F T naught. Convolution becomes multiplication. Fourier transform of the comb function will be 1 over Ts summation K delta. Oh, it's using N. Okay, so it's N. This is N. Delta F minus N over Ts. All right, so I can clean this up. All right, I bring everything inside here. I can get summation N T naught over Ts sync of F T naught delta F minus N over Ts. And then for the delta is 0 everywhere except at 1 over Ts, 2 over Ts, 3 over Ts, the delta. Okay, so that means wherever I see F here, I can replace by N over Ts. N over Ts, T naught. So that's my YF. All right. So that's part A. Part B is to find the spectrum of XS. XS is the product of X and Y. So we already found what is the spectrum of Y. Okay. So XS, of course, we do not know what is X because we are not told what is X. X can be anything. Anyway, SX is XT times YT, right? Okay, that means capital XS, F will be whatever is XF. We do not know what it is. Convolve with YF. Okay, convolve with YF. All right, so YF, you know, is this guy. So it's XF convolve with YF. All right, so that will be XF convolve with summation of K and T naught over TS sinc of N over TS T naught delta F minus N over TS. All right. So what happens is that when you bring the XF inside here, you convolve its replication property. So wherever you see F, you will replace by F minus N over TS. So that will be summation N T naught over TS sinc of, this is still the same, TS and T naught, X of F minus N over TS. Okay, that's what we have. All right. Because it's replication of X at all these locations of the delta. All right, so we found expression XF in terms of X. And then it says, find the minimal Fs such that X can be reconstructed. The minimal X such that a minimal Fs, sampling frequency. Such that it can be reconstructed. So what happens here is that you have whatever is XF, we do not know what's the spectrum, but let's suppose it's a low pass signal. All right, and you're told that the bandwidth of X is B, as you can see here, is B. So now you have this X, which has B, and is replicated every delta at 1 over TS. 1 over TS is Fs. So if you don't want to have aliasing, the minimum Fs must be 2B, no? Twice the maximum frequency. So Fs minimum value of Ss is 2B because the bandwidth of X is B. All right, the bandwidth of X is B. Okay, so to give you some insight as to what is actually happened, if you were to actually plot this guy out, this XS, it would look something like that. How should I put it? Okay. You have this sinc function, which is like an envelope, huh? Okay, which let me draw it this way. Okay, let's see the sinc function. Let's draw it because it's supposed to be much bigger. That's the first kind, huh? The main lobe, huh? And then whatever is XF is replicated. So you have that, this replicated. So the height of this is controlled by this T naught over Ts sinc of this, the height. All right. So I'm drawing an FS where it is an oversample because the bandwidth of this signal is B. So this is B here. This is B minus B. That's the bandwidth. All right. So if you don't want to avoid aliasing, all right, avoid the aliasing, then FS must be at least 2B, 2B, so that they don't overlap. All right. And then he says the last part, if the minimal value of Fs is applied, indicate the ideal reconstruction filter gain. All right, so you can see that this signal here, the center part here is scaled by this guy here, T naught over S, because when n equals to 0, sinc of 0 is 1. So the height here is here, the height here is T naught over Ts. So if you want to recover back the original signal, you need an ideal low pass filter of bandwidth B and a gain of Ts over T naught to cancel out the T naught over Ts here. So the recon filter is a low pass filter with cut off frequency of B and gain of Ts over T naught. Okay, so the Ts over T naught times T naught over Ts will bring it back to 1. So that's part B. Regarding which lecture? Lecture 5, sampling. Okay. Yeah, it's regarding chapter 5, sampling theorem. Yeah, and again, this is again in the summary, which is called lesson 24. All this is inside there. We spent about close to 2.5, 3 hours, if I recall. Yeah. Okay, so please, if you're doing revision, just have a look at those two because it summarizes everything, those two videos. All right, so that was number 5. Is that okay?
Prof.
Mm-hmm.
When the last question, right? The ideal recon filter is a low pass filter, not a band pass.
Low pass, this is a low pass signal.
Oh.
I'm recovering back X.
So, but if low pass signal, that means you only get the positive side only, right?
What positive? Your low pass filter is this guy lah. Bandwidth of B.
Oh, okay.
Okay. Any other question? Actually, we did the whole paper already almost. 5, 6, 7, 8. How do I get the gain? Because when n equals to 0, which is this guy here, when n equals to 0, sinc of 0 is 1. So what happens to x? You can see that xf is multiplied by t naught over ts. That is the signal xs. So if I want to get back x, I have to compensate for this t naught over ts. That's all. That's how the gain is of the filter. T naught over ts times ts over t naught is 1. Okay? Anything else? Any other questions? No? Nothing? All right, if nothing, then we can end the session. So again, strongly advise you guys to review the two videos, video 24 and video 25, which summarizes all the key points in signals and systems. Okay?
Prof,
Yeah.
can I ask question on your assignment?
What is the question?
The last question.
What is this? I have to stop and pull out the assignment. Just give me a minute. Where is it now? Hold on now. I'll be marking all your assignments and completing it this weekend. Assignment. I have the assignment here. Where did I put it now? Hold on. Okay. Okay.
Yeah.
Yeah.
Yes. So the thing is that okay, so we have the transfer function, right?
Mm-hmm.
And then the input is 30 UT, right?
Yeah.
And then
The
we
desired angle is 30. That means
yeah.
you're given that theta r is 30. Yeah.
Yeah. So we want what is the output, right?
Yep.
So in a stable system, the output should be finalized to 30, right?
No, doesn't necessarily. Depends on what the function is. I cannot remember now because I have to look at solution.
The transfer function is theta over theta r.
All right. Hang on. Let me just share this. Let me just quickly have a review of the thing first. Just give me a minute. Yeah, your transfer function based on the input as a step, because you already have reduced the system to a second order system.
Yes, yes. Because
And the second order system is an underdamped system.
yeah, correct.
So it's a decaying sinusoid.
Correct.
So that's what you're supposed to sketch.
Correct. So you will go to 30, right? By right.
Depends on your alpha. Depends on your alpha.
Yeah, you'll be close to that. I mean, it's 30.
No, whatever is your alpha. I will not say close or not close because different people have different alpha.
Oh, yeah. Sorry.
You cannot assume
yes,
like that,
yes.
Because everybody you have a different number for alpha.
Yes.
Okay. Let me put back the screen first. Yeah, hold on. Hold on.
Yes, but the question I want to ask is that we assume the initial condition is 0, right? For this case.
Yeah, because he already told you what is theta r.
Yeah, correct. But the thing is that the heading might not be initial condition is 0. It could be any other thing, right?
Yeah, line is okay lah. If it's not 0, then your sinusoid at t equals to 0 will not start at 0 lor.
Correct lah. So what I mean is that for this question, we'll assume it's 0, right?
Can lah.
Okay. Can. That's all I want to ask. Thanks.
Yeah. Any other question?
Prof.
Yeah.
One last short question regarding the signal question.
Yeah.
Example, normally sometimes they will give like a low pass filter given like HF is equal to rec of F over 12. Example. Yep. So that means we filtered between -6 to 6.
Yep. So
but the problem yes, but the problem is how about the height? Example, the original signal height is
rec is 1 what?
Yeah, but your rec is only 1. So is there any impact?
Yeah, it just changes the height. Depends. If it is 6 rec, that means the height is 6. If it's just rec, the height is 1.
Because I see like question is only normally is given rec F over 12. So that means I assume the rec height is 1.
Yeah. If you draw, it'll be 1, isn't it?
But for 1819 semester 1, question 6, right? The height is 4, the original.
Then the height is 4. That means the filter has a gain of 4. That's all.
Oh, so we base on the original, not just filter and restrict the height at 1.
Whatever the question tells you. So in this case, the low pass filter has a gain of 4.
Oh, okay.
Okay.
Okay, thanks.
Anything else? Okay, so all of you would have received your emails regarding the exam already. And in the emails, we also sent you the attachments like the cover sheet, the declaration, and so on. All right, so in preparation for the exam. Okay, so remember, exam is on the 30th at 2:30. So come in earlier to prepare yourself. Come in earlier, settle down. Then we can carry out the exam on the 30th of April. All right, so that is next Friday, I think. Yeah. Okay, anything else, anyone? All right, if not, then we can end the session. If you still have questions, you can email me. Nah? All right, all the best to all of you. Take care. All right, bye.